Today we're going to talk about functions and inverses. Functions. The formal definition of a function incorporates a set of inputs, the function rule, and the set of outputs. A function consists of a set of inputs called the domain, a rule by which each input determines one and only one output, and a set of outputs called the range. The examples below list inputs and outputs for two relations, determine whether each relation is a function. So looking at the first one, we have inputs 1, 2, 3, 4, and the outputs are 8, 7, 8, 9. So notice that the outputs are repeating, but the inputs are not. So for each input, we have only one and only one output. So yes, this is a function. And you can also confirm that by looking at the graph. So if I were to graph it, you would get something like this right here. And of course, this would pass the vertical line test for each of these 4 points that we have. So that also confirms that it is a function. Looking at the next one, so we see we have 10, 12, 11, and 10. So here we see that we have repeating inputs or repeating x values. So each input does not have one and only one output because this has an output of 8 and this one has an output of 11. So no, this is not a function. We can also confirm that by looking at the graph. So if I graph those points, I can see that right here, this is the x value of 10, and we have the two different values, 10, 8, and 10, 11. So this would not pass the vertical line test. And so therefore, again, it's not a function. So now we're going to evaluate our functions. So find the indicated values of g of x. So given the function g of x equals x squared plus 1, we want to find g of 3. So remember, that means that you're plugging 3 in for each value of the equation for x. So 3 squared plus 1. So when I do that, I get the square root of 9 plus 1, which is the square root of 10. Anytime that you can reduce a radical, you always want to reduce it. Do not write the decimals of them. Now that we're in pre-calculus, we always want to write exact value answers when possible. So we always just use reduced radical form. So this does not simplify any further. So that would be my solution. Looking at the next one, we have the square root of -5 squared plus 1. So we're squaring the negative because that's what we're plugging in for x. So that becomes positive 25 plus 1, and then that gives us the square root of 26. Again, you would see if you could reduce this, which this does not reduce because this factors into 2 times 13. So there are no groups of 2 to take out. So that's why root 26 is my solution. Here I get the square root of 0 squared plus 1. So this is the square root of 1, which is just equal to 1. For the next one, we're going to use the function f of x equals x squared minus x plus 2, and h of x does not equal 0. Find each output. So for this one, if I plug 2 in for x, I get 2 squared minus 2 plus 2. So that gives me 4 minus 2 plus 2, which is equal to 4. Here, if I plug in 3 squared minus 3 plus 2, so 9 minus 3 plus 2, which gives us 8. Over here, f of x, so they gave us f of x, that was the original problem, so f of x is just equal to x squared minus x plus 2. So then here, now the difference is instead of plugging in just a number like we did here, we're plugging in x plus h. So we're actually plugging in this whole thing in for each x. So that's where it gets a little bit trickier because you have now not just numbers that we're plugging, but also numbers and variables, or just variables in this case. So we get x plus h quantity squared minus x plus h plus 2. Here we have a binomial squared, so that means you want to FOIL that out. Because remember, we can't just use the properties of exponents when you have addition or subtraction sign in between. So here, distribute the negative, so we get minus x minus h plus 2. When we FOIL this out, we get x squared plus xh plus xh plus h squared, minus x minus h plus 2. And then these are like terms, so x squared. And then we also have that plus h squared plus these two become 2xh minus x minus h plus 2. And then you would combine like terms, but there are no like terms to combine, so that would be our solution. So here we're taking f of x plus h minus f of x. So our answer from a previous one, which was x squared plus h squared plus 2xh minus x minus h plus 2, and we're subtracting that from f of x, which is x squared minus x plus 2. So you have to distribute that negative to each of these terms. And then, of course, you want to combine like terms. So we have x squared and negative x squared, so those cancel out. We also have negative x and positive x, which cancels out. 2 and negative 2 cancels out. So what are we left with? H squared plus 2xh and then minus h. Functions defined by equations. Equations in two variables can be used to define functions. However, not every equation in two variables represents a function. Determine whether each function defines y as a function of x. So looking here at this first one, we have x squared plus y squared equals 16. So if we want to determine whether or not each function defines y as a function of x, that means we need to solve for y equals. So here is my y, so I'm going to solve by first subtracting x squared to the other side. So I get y squared equals negative x squared plus 16. Those aren't like terms, so I can't combine them. Here I have to solve for y. To get rid of that power, I take the square root. So y is equal to plus or minus the square root of negative x plus 16. So now this is not a function because we have the plus or minus. So this plus or minus means that for every input, we have two output values. So it's not a function. So over here, if I solve, same thing's going to happen. I'm solving for y. I have that y squared. So y is equal to plus or minus the square root of 4x plus 1. So this is not a function. Here, y is already solved. And so this is a function. It's a quadratic equation. Y equals 4x squared plus 1. So this is quadratic. And so yes, it's a function. You could even graph it. If you think about the transformations that we learned last year, what happened to this graph? So this was a vertical stretch by 4 and moves up 1. So if we were to actually look at this graph, it would look something like this. And of course, that passes the vertical line test. So anytime you're looking at graphs that we know, you should always think about the transformations. Looking over here, we have y to the fourth is what we're solving for, the y equals. So first get rid of that 4x by adding it to the other side. And again, we're getting rid of a power 4. Anytime you get rid of an even power, you always take plus or minus the square root. If it was odd, you do not, but for even, we do. So this is plus or minus, in this case, not the square root, but we're taking the fourth root to get rid of that power 4. So the fourth root of 4x plus 1. So because of this plus or minus, this is not a function. So really, anytime you're solving for y equals, and if your y has an even power, you know that it is not going to be a function. One-to-one functions. A function is one-to-one if every output corresponds to exactly one input. If a function is one-to-one, then its inverse is said to be a function.
We can also, in order to tell whether or not a function is one-to-one, use the horizontal line test. A function is one-to-one if and only if no horizontal line intersects a graph of f more than once. So if you look at this horizontal line I drew in this first graph that we have, you can see that this does not pass the horizontal line test. Therefore, I know when I am going to graph the inverse that it is not going to be a function, because this problem says we want to graph the inverse, describe the relationship between the function and its inverse, and write the equation for the graph. So again, I know that this is not one-to-one, that it doesn't pass the horizontal line test, and thus the inverse is not going to be a function. So remember, to graph the inverse, we would want to switch our domain and our range, or x and our y's. So the first thing I did was pick these point values, and I made a table for x and for y. So then, of course, if we recall from the inverse, and remember that's your inverse function notation. So for this, we take these y's, they now become my x's. And then these x values would become my y's. And then the next thing I'm going to do is just going to actually plot these points and then sketch the graph. So I just plotted the points from the table, and then now I'm just sketching the graph. And as you can see, we remember from last year we also did the vertical line test, so now you can actually use the vertical line test to confirm what we said earlier about the horizontal line test and show that this doesn't pass the vertical line test and therefore is not a function. Okay, the last part of this says we want to write the equation for the graph. So I'm going to use the fact that we just talked about transformations of functions, and we know this is a quadratic function, so the parent graph is x squared. And for this, I can see my graph has moved to the left 3 and down 4. So we get y is equal to x plus 3 quantity squared minus 4. And that would be the equation for the graph. Now, if I wanted to find the inverse for this, that's what we're going to do next. We actually, if you recall, switch your x and your y values and then solve for y equals after you switch them. So looking at this, remember that means you are really going to be doing your order of operations in reverse. So PEMDAS. So if I look at this first equation that I have, I first switch my x and my y values. So I get x is equal to 3y minus 2. The next step would be to, do the order of operations backwards. So I want to add that 2 to the other side to get it away from the y. And then the last step would be to divide both sides by 3. So now I get y is equal to x plus 2 over 3. This is just linear, so I know it is a function. So because it's a function, I can actually use my function inverse notation. So f inverse of x is equal to, and we can just separate those. So x over 3 plus 2/3. So then for the next one, we're going to be doing the same thing. So again, switch your x and your y. So x equals y cubed minus 5. We're doing the order of operations backwards, which means I don't want to get rid of that exponent until after I get rid of that 5. So I want to add that to the other side. So we get x plus 5 is equal to y to the third. There was no multiplication or division, so now that's why we're at the exponent. So we get rid of the exponent. We want to take the cube root of both sides. So this would be the cube root of x plus 5. And the cube root of y cubed would just be y. And again, now I can go ahead and use my inverse function notation to get my inverse equation. So in this next one, we're going to do the same thing. Switch our x and our y's first. So x equals y squared plus 4y. This one's a little bit harder because we have a quadratic term, a linear term, and this x over here. So for this one, I actually can't divide a y out because that's not going to help me, and I can't factor a y out because that doesn't help either. So in this case, you would actually want to set it equal to 0 by subtracting the x to the other side. and you would actually want to use the quadratic formula in order to get y by itself. So if you recall, the quadratic formula is negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So in this case, my a value is what's in front of my quadratic term, which is just 1. My b value in this case is equal to 4, and my c would be this whole last term, negative x. Because again, remember, we're trying to write the inverse equation. So now when I plug that into my quadratic formula, I get y is equal to not x, because again, we have y here, and that's what we're trying to solve for. So y is equal to negative 4 plus or minus the square root of b squared, which is 4 squared, minus 4 times a, which is 1, times c, which is negative x, all over 2 times a, which is 1. And then we're going to just go ahead and simplify this. So we have y is equal to negative 4 plus or minus the square root of 16, and the negative times the negative becomes positive, so plus 4x all over 2. And then notice here the 16 and the 4 have a common term, which is 4, so I'm going to factor that out. So I get y equals negative 4 plus or minus the square root of 4 times 4 plus x all over 2. And the reason I did that is because I know the square root of 4 is 2, so that's going to help me take it outside the radical so I can simplify further. So y is equal to negative 4 plus or minus 2 times the square root of 4 plus x all over 2. And now I can go ahead and separate my terms to simplify further. So y is equal to negative 4 over 2 plus or minus 2 root 4 plus x, or you could write x plus 4, doesn't really matter what order you write that in, divided by 2, and now I can simplify. So I have y is equal to negative 2 plus or minus, these 2's would cancel out, so root, and I'm going to write this with x first, so x plus 4. And this is not a function because we know that for every input we have the plus or minus there, so we would have 2 output values for that. And I'm going to go ahead and move this so it's not in our way for the next problem. So then for the next problem, we're of course going to do the same thing. So first thing we want to do is switch our x and our y values. So we get x is equal to 2y over y plus 2. Now for this one, because it's in my denominator, I want to get rid of that by multiplying both sides by y plus 2. And when I do that, because this is really over 1, then I can go ahead and cross these off. So now I've gotten rid of it to the other side, and I can distribute. So I get xy or yx plus 2x is equal to 2y. Then because I have y's on both sides, I'm going to want to leave the 2x on one side and get the y's together because I noticed they're both linear, so it means I wouldn't be able to factor it out. So I'm going to have 2x is equal to 2y minus x times y. And here, again, because these are both linear, I can factor those out to get it by itself. So 2x is equal to y times 2 minus x. And then the last step is to get y by itself. So this is all being multiplied by y. So to get it by itself, you want to divide it onto the other side. And now notice y is by itself because that would cancel out. So we get y is equal to 2x over 2 minus x. And that would be my inverse equation. So as you can see, these do get a little bit harder as we are now in pre-calc. So for the next part, it says when you're solving an inverse equation and you need to take both sides of the equation to an even power, you need to restrict the domain by looking at the original function's range. So restricting the domain, we're going to talk about that. So for a function that is not one-to-one, it is possible to produce an inverse function by considering only part of the function that is one-to-one, and this is what we call restricting the domain. So let's work with something that we're familiar with, which is y equals x squared. So we know that if I were to graph this, we know what it looks like, and we know that this is not 1-to-1 because it doesn't pass the horizontal line test, therefore the inverse would not be a function. So we're going to purposely pick our own values to restrict it to make it 1-to-1, and then find the inverse over that interval. So if it's a quadratic, the easiest thing to do would be to actually figure out where that vertex is, and we know since our parent graph, our vertex is at 0, 0. So I could restrict my graph just to this part that I highlighted and take off this other part in blue, and then it would pass the horizontal line test. So that's one way I could restrict it, or I could restrict it to the right side and take off this part that I highlighted in yellow on the other side. So either of those would work. So let's go ahead and first actually figure out what the inverse equation is. So switch our x and our y. So x is equal to y squared. So get rid of that power, I have to take plus or minus the square root. And now I have my inverse equation. So when I have the negative part of my equation, that would be this side of my graph. So this would be the y equals negative root x. And this side of my graph is actually the y equals the positive root of x. So if I'm writing this out, I would say restrict f of x domain, and we're going to do negative infinity to 0 bracket. Then our inverse, so f inverse of x, would be equal to what we just said over here, the negative square root of x. So that's one possible answer. The other possible answer would be to restrict f of x's domain to bracket 0 to infinity, because that was the green side that I highlighted. Then f inverse of x would be equal to the positive square root of x, and you don't really need that positive there, so you could just write the square root of x. So those are two possible answers that I could write for this question. Then if I look at number 2, we're going to do the same thing, except we're going to use a different function. Well, same function, quadratic, but we just did a transformation moving it down 3. And actually, let's change that so that instead it would be x minus 3 quantity squared, because then we're actually going to change that interval that we had, because that would move our graph to the right 3. So this is my function. And I've now moved this to 3, 0. So then if I wanted to restrict those values, I could restrict it to this side, or I could do this side. But notice now that the value that I'm restricting it at, the vertex area, is right here at 3, 0. So I could say the first thing I want to do is figure out the inverse. So we get, of course, this was y equals, so first switch those values. So x equals y minus 3 squared. And then order of operations backwards. So in this case, we have to get rid of that exponent before we can do what's in here. So we have plus or minus the square root of x is equal to y minus 3. And then the next step would be to add that 3 to the other side. So y is equal to 3 plus or minus the square root of x. So that means, remember, we have two equations. We have y equals 3 plus the square root of x, and y is equal to 3 minus the square root of x. So if we're on the left side, we're going to use this equation, and on the right side of our domain restriction, we're going to use this first equation. So we could say restrict f of x domain to negative infinity to, and now we've moved it to the right 3, so 3. Then f inverse of x would be equal to the negative square root, so 3 minus the square root of x. So that's one possible answer, or we could say restrict f of x domain to bracket 3 to infinity. Then f inverse of x would be equal to the positive square root, so 3 plus the square root of x. And question number 3 says find an interval in which the function f of x equals the absolute value of x is 1 to 1, and then we're going to find the inverse on that interval. So if we use our horizontal line test, we can see that this does not pass the horizontal line test. So because it doesn't pass the horizontal line test, we know the inverse is not a function. We can restrict our domain of this function in order to make the inverse a function. And again, we can use either the negative or positive of the absolute value side. So this would be the positive side and the other side is the negative side. And we know that this original graph, the domain of f of x is all real numbers. So we are restricting that so that we can have an inverse that is a function. So we can either use the domain from negative infinity to 0, or we can use the domain from 0 to infinity. So if I either cut off this left half or the right half, then it would pass the horizontal line test. The range of this function is, of course, from 0 to infinity. So the next thing we need to do is find the inverse. So to find the inverse, remember, we switch our x and our y values. So this would be y equals the absolute value of x. So if we switch these, we get x equals the absolute value of y. So how do I solve an absolute value equation? So recall, we've learned how to solve such equations like the absolute value of x equals 7. We solved these in Math 2, and we also solved these last year. So if I want to solve this, I know that I have two cases. I have one where we had the positive answer and the negative answer. So x would be equal to 7 or x equals negative 7. And then we did more complicated equations. So like if I had the absolute value of x plus 2 is equal to, let's say, 7 again. So if I were solving this equation, we would say x plus 2 equals 7 or x plus 2 equals negative 7. And then I would solve by subtracting the 2. So x equals 5. Or if we subtract the 2 over here, we get x equals negative 9. And then, of course, you could check your answers. If I plug 5 in, 5 plus 2 is 7. The absolute value of that is 7. If I plug in negative 9 plus 2 gives me negative 7. The absolute value of that is 7. So that's how we solved our absolute value equations. And so over here, in order to solve or get the y out of the absolute value, I have to set up my two equations. So we would get y is equal to the absolute value of x, or y equals the negative absolute value of x. And so now I can write my answer. So we say restrict f of x is domain 2 if we use negative infinity to 0. Then f inverse of x is equal to, and if we're doing the negative side, we would use negative x, or we could restrict f of x is domain 2, 0 to infinity. Then f inverse of x is equal to the positive x. Now, for this, you have to be careful. So remember, when you find the inverse of something, you switch the x and y's and then you graph. So if we were to graph the actual absolute value inverse, one side would go this way and then the other side would go like this. So it'd be a V looking like it's on its side going like this. Now, notice that that means we don't have this full equation y equals negative x or y equals x. Notice that the domain values are restricted from 0 to infinity, because remember, when you find the inverse, you're switching the domain and range, so you're switching your x and y's. So that means that from f of x, remember that we said this was the domain in the range of f of x. So if the range is from 0 to infinity, then that means my inverse graph, I need to restrict those x values from 0 to infinity. So this would be, again, now I have to restrict the domain again, which makes this one a little bit harder. So this domain we would say is then from 0 to infinity for both of them. So that would only give us this part of the line and this part of the line. Because again, remember, you switch your domain and range values. And that's it.